Hey, hi everyone. So in the previous video, I already discussed the idea of electric potential by relating it to electric field. So the presence of these two concepts is to explain why even though the two charges are not touching each other, they are able to interact. So we need the presence of electric field so that the forces we can have electric forces acting in between two charges. So we need electric potential because electric potential allows us to explain why even though two charges are not touching each other, they are able to share the electric potential energy between them. Okay, so I hope you can see some sort of similarities between these two concepts over here. But now that we have already have a rough idea of electric potential, I would like to sort of visualize a bit the idea of electric potential a bit further and to head it into the direction of potential difference. Okay, so visualizing the idea of potential difference. Okay, previously we are talking about electric potential, so now I'm going to head towards the direction of potential difference. Okay, so imagine today, let's say you have a charge, and this charge is maybe a positive charge. Sorry. Let me say that, let's say initially, okay, I'm going to write the word initial, just be very clear. Initially, I have a situation in which I have a positive charge, which is placed over here, and let's say the name of this charge is Q. And this is the situation right now, and the negative charge, which is small q, is now being placed at this position over here. See, right now it's at this position q. Okay, and we can say the distance between them right now, let's just keep it simple and call it as Ri, which is R initial. Okay, so I'm going to label this place at as position X. This particular point, I'm going to call it as position X. Okay, now what I'm going to do is I'm going to move this charge with constant velocity. Actually, I'm going to move this charge to a new position. Let's say Y. Okay, so this charge Q is being moved from position X to position Y. Okay, we're going to move. Okay, so the final situation here, what happened to my handwriting today? The final situation that I'm going to have right now is my positive charge big Q is going to stay at its original position. I'm not doing anything to it. So Q will remain at this position. But right now my negative charge small q is now being moved to a new position over here. Okay, so position X and position Y are still the same place. Okay, this is still position X, this is still position Y. But right now the charge has moved from position X, it has moved to position Y. Okay, so right now the distance between them, I'm going to call them as RF, representing the final distance between big Q and small q. Okay, so what I can say for this particular situation is, at this position, in this position, both of this position, there's electric potential which is produced by Q at both positions. Okay, if you are at position X, there's electric field, there's electric potential produced by big Q. Okay, big Q is over here, so the surrounding of big Q with electric potential produced by big Q, right? So position X here has an electric potential produced by big Q. Position Y over here will also has an electric potential produced by big Q as well. But the strength of the electric field at these two positions might be different. Okay, point X has its own electric potential strength. We don't call it electric potential strength. Okay, point X will have its own electric potential. Point Y will have its own electric potential, but both of these electric potential exist because of the presence of big Q over here. Okay, so what happened right now is Q is initially interacting with the electric potential at X. Okay, okay, of course this electric potential at X, I have to emphasize once again, this electric potential at X is produced by Q. Okay, so because this small q over here is interacting with the electric potential at X, and this electric potential over here is produced by big Q, there will be the response of this interaction is big Q and small q will share a electric potential energy together. So that is represented by this spring over here. So I'm going to call this as U between big Q and small q initial. Okay, so what happened at the final situation is Q is no longer at X, Q has moved to Y. So Q is finally interacting with the electric potential at Y. Okay, again, this electric potential is also produced by big Q, because big Q stays at its place. Okay, but this electric potential at Y and the electric potential at X are two different electric potential values. Okay, the values of electric potential at X and Y are different. Okay, so what we can say is we can find the difference in electric potential between these two positions. Okay, because we know that both of these positions has electric potential, but the electric potential of these two positions, they are different. So you can find the difference between these two positions electric potential. Okay, and this difference in electric potential between two positions is what we call as the potential difference. Okay, so that's why we talk about potential difference. We're not talking about the change in electric potential at the position. I'm not saying that the electric potential at Q, the electric potential at X is initially weak. Then after some time later, the electric potential at X becomes stronger. No, this is not the kind of difference that I'm talking about. The potential difference that we are talking about over here is the potential difference between two different locations. Let's say position X has an electric potential, position Y has an electric potential. So if you find the difference between the electric potential of these two positions, that value, the difference that we found, is called the potential difference. And in later stage in other chapter, we are going to change this potential difference word to become voltage. So voltage is the same thing as potential difference, and potential difference is actually just a difference of electric potential between two different positions. Okay, so when the charge small q reach the final position of Y, charge small q over here is interacting with the electric potential at Y right now. So because of that interaction, it will also experience a electric potential energy share between big Q and small q. But as you can see, the length of the spring is different already, so the amount of electric potential energy shared between them will be different as well. So you can see the change in the electric potential experienced by this small charge Q over here. Okay, the change in the electric potential experienced by the charge going from position X to position Y will cause a difference in the, or cause a change in the electric potential energy experienced in between these two charges, big Q and small q. So if we can look in this situation over here, we can see that for general cases, most of the cases, we can sort of see that, okay, I'm not saying that for all cases, for most of the cases, or for most of the questions that you find in an exercise, we can see that the moving charge is usually the interacting charge. So it's interacting with the electric potential at different positions. Okay, whereas the stationary charge, which is a non-moving charge, okay, you can see big Q over here is stationary, is not moving, right? So these charges are actually the charge that is producing the electric potential. Okay, I'm not saying that this is applicable for all cases, but if you're looking at a situation, you're not sure who is producing the electric potential, who is interacting with the electric potential. So in this case, you can sort of use this generalization method in which you think that, oh, the charge is moving, this charge will be the one that is interacting with the electric potential. Oh, this charge is not moving. So this not moving charge will be responsible for producing the electric potential, then the other charge will be interacting later. Okay, so this is sort of an idea that I want to tell you right now. Okay, so I hope you all can see the idea of potential difference clearly right now. It's that one position has a certain electric potential, another position has an electric potential. If you find the difference between them, the value here is called potential difference. That's why, okay, I'm slightly steering off the topic a little bit. That's why if I okay, that's why if I talk about, let's say, I'm just any kind of experiment, okay, in experiment, you notice that if you're talking about an electric circuit, let's say with a resistor over here, okay, you notice that you will install the ammeter, the one that is measuring the current, you install it in series with the circuit. But you notice also that you are installing the voltmeter, which is measuring the voltage of the potentiometer, parallel to a certain load over here. Okay, so I hope you can see that the installation method of the voltmeter, which measures potential difference, voltmeter connects to the circuit at two different points. Okay, you are connecting at two different points. Why do you connect a voltmeter at two different points? It's because you're finding the difference in V between the 2 points. That's why you connect a voltmeter at 2 points of the circuit. Okay, ammeter just connect it in series, so you are measuring the current flowing through it. That's why you just install it like this. But if you're talking about voltmeter is measuring voltage. So voltage is potential difference. So potential difference means what? You're finding the electric potential between two locations. So which two locations? One end and two end of the voltmeter. So they measure the two electric potential, find the difference, and that's the potential difference. Okay, so that's the idea of potential difference. It's based on two locations. Okay, so now we know the idea already. Let's sort of formalize it a little bit. Okay, I'm sorry for a long-winded explanation. It's just that I don't think students can immediately see the idea of potential difference really clearly. That is with respect to two locations instead of the changes with time. Okay, it's two locations. Okay, so right now I'm going to talk about potential difference for real. So what is potential difference? Potential difference is just the difference in electric potential between 2 points. Okay, so here I'm going to give you a scenario. Okay, so let's say today you have, let's say Q1 over here. And let's say you have Q2 over here. Okay, so let's say if I want to find the electric potential at X, I want to find electric potential at Y. If I want to find the electric potential at Z, how will I find the electric potential V at position X? Okay, we know who is producing the electric potential at X. The electric potential at X is produced by Q1 and Q2. Q1 is over here, it produces an electric potential around it. Q2 is here, it produces an electric potential around it. So at position X, there will be electric potential produced by both Q1 and Q2. So if we add up the electric potential produced by each charges over here, we are able to find the electric potential at X. So what do I usually do? Let's say if today, let's say if I'm finding, let's use a different pen. Let's say if I'm finding electric potential at X, what I would do is I'll draw springs, connect the charge that produce the electric potential to the point that I'm interested in. So one is from Q1 producing the charge to the point that I'm interested in X. Another spring will be from another charge that is producing the electric field Q2 to the point that I'm interested in X. Okay, so this one I'm going to label it as KQ because this is produced and we're going to use a produce equation KQR. So who is producing? Q1. So this one will be KQ1. The distance will be between, sorry, the distance will be between Q1 and X, right? So R1X. Okay, whereas this one, the distance will be between, this is produced by Q2, this will be distance between 2 and X. Okay, so when you know that Vx can be found by adding up these two springs electric potential, KQ1 over R1x plus KQ2 over R2x. There are two charges that produce, I just need to add them up. Because there's no direction, I don't need to do x-axis, y-axis, x component, y component, Pythagoras, tangent, theta. I don't need to do all those things. This is a scalar quantity, I can just add them up. Okay, but remember Q, there's no modulus, so put in the sign of the charge as well. Okay, now let's say I want to find the electric potential at position Y. So position Y is over here. So what I can do is I can draw charges, springs connecting the charge that produce the electric potential to the point that I'm interested in. So Q1 is producing the electric potential. Y is the point that I'm interested in. So this will be KQ1 over R1y, distance between charge 1 and Y. Okay, another charge that is producing the electric potential will be Q2. So I'm going to draw a spring connecting Q2 to Y. Then this is KQ2 over R2Y. Okay, so these are the two charges that are responsible for producing the electric potential at Y. So if I sum them up, I can say Vy is just equals to KQ1 over R1Y plus KQ2 over R2Y. Okay, so this is how I find the electric potential at Y. How about Z over here? Z over here is directly on top of Q2. As we discussed about electric potential or electric field, you cannot produce an electric field or you cannot produce an electric potential right at the position that your charge is at. So Q2 is over here. Q2 can't produce an electric field or electric potential at the point where is it. It can only produce an electric field or electric potential around the charge. Okay, so here there will be no electric potential produced by Q2. So if there's no electric potential produced by Q2, there's only electric potential produced by Q1. There's only one charge that is producing the electric potential over here. So maybe I use green. Okay, so there's Q1 producing the electric potential, and the point that I'm interested in is Z. So if I find Vz will only be one spring only, which is produced by Q1. This is R between charge 1 and position Z. Okay, there's no two springs over here. For position Z, there's only one spring. So I'm going to add KQ1 over R1Z. Okay, so this is how I find the electric potential at three different points, X, Y, and Z. But now I'm not just interested in the electric potential. I want to find the difference in electric potential between any 2 points. So I can find the difference in electric potential between X and Y, Y or Z, or X or Z. Okay, anything like that. Okay, what I'm going to talk about is the confusion that many students might have when we talk about potential difference. Because the wording that the question used when we talk about potential difference can be confusing. So here I'm going to give you a few examples of the wording that we usually use when we ask about potential difference. So you can know clearly what steps should you do to find the difference in electric potential. Okay, so ways to ask about electric potential. Okay, so the most common way that we see in matriculation questions, okay, I'm saying in matriculation context, the most common way of asking potential difference is they say what is the potential difference. I'm short forming it as PD. Okay, potential difference between, let's say, X and Y. And actually this is the kind of wording that I don't really like. I don't really prefer when people ask between X and Y. Okay, so first of all, we have to be very clear that when we talk about potential difference, the symbol is Let me be very clear and write it up on top. The symbol for potential difference is delta V. Okay, why didn't I write it in the first place? The difference in the potential difference, the symbol is delta V. Okay, so I hope you are clear that when we see delta V, right, it's always final minus initial. Okay, of course, let me add some information. The unit is still volt, because you take final electric potential minus initial electric potential, still the same unit. Okay, so where's my cursor? Okay, so because this is the symbol for potential difference, or because the idea is potential difference, delta V here must always be final minus initial. Okay, this is final, this is initial. Okay, it should always be like this. It should always be the final electric potential minus initial electric potential. If you look back at the case over here, we are moving from x to y, right? So the final electric potential will be the potential at y. The initial electric potential will be the potential at x. It's quite clear cut if you look at the situation. But if the question just asks what is the electric potential between x and y, the word between here doesn't carry any form of direction. If I ask you what's the distance between KL and Sabah, does it mean I go from KL to Sabah? Or does it mean I go from Sabah to KL? It doesn't carry any meaning of direction. Right? I'm not going from where to where at all when I say the word between. So in this case, it can be a bit confusing who will be taking the role of the initial, which position will be the initial position, which position will be the final position. Okay, and it's because that it's confusing and there's no sense of direction to the word between, that it is my opinion, based on my understanding, and based on what I refer to many international books as well, my opinion will be, if you see the word between, if you choose to write it as Vx minus Vy, if you choose to write it as Vy minus Vx, in my opinion, my name is Gan, in my opinion, both should be equally acceptable. Okay, both should be equally acceptable. So because there's no sense of direction, so they are not being specific, so I think both answers should be acceptable. This is my opinion. Okay, but just want to tell you that certain college or certain lecturer, let's just call it lecturer A, might only allow you to use the first method, might not allow you to use the second one. Okay, and certain lecturer, let's just call it as lecturer B, might allow you to use the second method but not using the first method. But in my opinion, both are equally acceptable because there's no sense in direction to the word itself. Okay, so if you are not my student, okay, maybe you have from other classes, so if you just consult your lecturer to have a very clear idea which is the acceptable method. For me, I think both are acceptable. If you ask what is the exam standard, honestly, I myself got myself quite confused right now that I don't even know what's the current standard for between what and what. Okay, for me, I think both are acceptable. I don't think there's any reasoning to say why one is less acceptable than the other. Okay, if you ask between. Okay, I don't think there's any proper reasoning to say one is more acceptable than the other. So I'm going to say both are acceptable. Okay, but follow your own lecturer. Okay, it's not decided by me. If you follow your lecturer, what your lecturer say. Okay, I'm going to move on. The second way that we can ask about this is the potential difference experienced by a charge moving from X to Y. Okay, so there'll be a charge moving from X moving towards Y. So if you see this kind of wording where it says clearly that it's from where to where, then I don't think there's any kind of doubt that you can have over here. Okay, so in this case, I think it's universal that you should take the final, which is Y minus the initial, which is X. Okay, if you take the other way around, which is Vx minus Vy, that will be very much incorrect. This will be correct. Okay, because it's very clear that this one is the initial, this one is the final. So final minus initial, so Vy minus Vx. Okay, the third way, which is what many books usually use, is the potential difference of Y with respect to X. Okay, so this is potential difference of Y with respect to X. So that means we are going to refer to X as our basis, as our baseline. So how much is the electric potential of Y if we compare it with X? So X serves as our baseline. So whatever that serves as our baseline should actually be the thing that is at the back. So in this case, it's Vy minus Vx. That is acceptable. If you do Vx minus Vy, that will be incorrect. Okay, so what we have over here is actually this is X with respect to Y. Okay, so I hope you are able to discern carefully or read the question carefully to notice this kind of directional, the keywords for this kind of directional thing. So from there you are able to know who is initial, who is final, and conduct your final potential minus initial potential correct. Okay, so that's for potential difference. And before I actually end this section, the last thing I want to talk about for a short while is space. I'm going to just draw a bracket and just draw a small box and talk about it. Okay, this is, I think it's just logical. I don't think there's a need to explain much about it, but let's just talk about it. Okay, one thing you need to know is change in electric potential energy is equals to final potential energy minus initial potential energy. Okay, this is what we learned from here. Okay, we learned about change in potential energy over here, change in potential energy over here. So it's just final minus initial. Okay, but what I want to say is you can use this equation. If you shift the interacting charge to the left hand side, U will be equals to QV. U will be equals to QV. Okay, so what I can do is I can change this equation to be QV final minus QV initial. Okay, the Q I don't need to differentiate final Q and initial Q because it's usually the charge Q moving from an initial point to a final point. So you take Q, the interacting charge, multiply by the final position's electric potential minus the same interacting charge multiplied by the potential at the initial position. Okay, why do I explain like this? It's because they have the same Q, therefore I can factorize out the Q. This is interacting charge Q. So here we have Vf minus Vi. And because this is Vf minus Vi, we know this is just the potential difference that we have just talked about. So I can actually end up with this particular equation. So the change in electric potential energy is actually just taking the interacting charge Q multiplied by the potential difference delta V. Okay, so if you know this already, the second thing that you should know is that you have work elect is equals to, let's say from initial to final, is negative delta U. So if you look at it, you can actually change it to become negative Q delta V. Okay, the same thing goes for work done external actually. Work done external from initial to final. This time external means when there's no negative sign. But again, you can also change it to become Q delta V. So these are three important things that you should know about based on our discussion from the first video until now. We learned about delta U before this. Now you have the idea of potential difference. You can see that the change in electric potential energy actually depends on this equation Q delta V. So you can modify the equation for work done as well. Okay, I'm going to wrap up my discussion on electric potential energy and electric potential at this point. But if you notice, the only thing that I haven't discussed is the idea of equipotential lines and equipotential surface. Okay, but I should come back to those concepts in the next section. Okay, in the next section, I'm going to talk about uniform electric field and charges moving inside the uniform electric field. So at certain point where I find suitable, I'll bring in this concept of equipotential line and equipotential surfaces, which I'm supposed to discuss in this section. But I think it's suitable that I shift it to the next section, and find a good point to bring it in, because there's still some stuff that I need to talk about in the next section first. Only I bring in the concept of equipotential line, equipotential surfaces. Okay, I hope the explanation until now has been okay. So if there's any question, feel free to contact me about it. Okay, so that's it for this particular video. Thank you very much.